with a couple of announcements before we start with lecture 12. So since I'm getting emails about exam 2, so I decided just to give you the heads up. So check the syllabus for the date of exam 2. I already published on OWL 4 different e-exams, practice e-exams, the same as exam 1. As usual, start with the practice exams, not the intensive. The intensive are more to tackle the multi-steps, and you better do those after you mastered the reactions. Now, the study guide for exam 2, the reaction summaries, whether they are in a reaction map, non-inked and inked, so that you can print it out, then have a reference, are all in the handout folder on Moodle. Now the chapters that are included in exam 2 is 18, 19, and 20. So today we're gonna finish at 20. So in other words, by the end of the lecture today, or by the end of this week, it is a preferential that you will be up to date with the homework. So you should supposed to be chapter 18, you're already practicing chapter 19 and chapter 20. Now, one thing about exam 2, as you can imagine, that 19 has a lot of reactions, and it is very important that you master those reactions before you get to the exam. Step 1, level 1 is to know the reaction. So if you feel that you're kind of just still get confused with the reactions, please make sure that you know them. And one way to do that is to put the reaction map in front of you as you're doing OWL and keep referring to it 2-3 times. The fourth time, just put the reaction map away from you and start to remember the reaction. It's really crucial. I know there are a lot of reactions in 19 compared to the other chapters, but it is a key that you know the reaction, master them, and be it's just once you see the reaction, you know the reagent or the product. It doesn't need that much time from you to do it. Okay. Now, I didn't put the mechanisms included in here. Probably in tomorrow's lecture 13, I'll put the mechanism that will be included in exam 2. So the same as exam 1, where you're gonna take the exam and how to handle it, all the other details. So I'm not gonna repeat myself about that. So today's lecture, it's gonna be split into 2, chapter 20. In yesterday's lecture, we talked about the reactions of carboxylic acids, how to prepare them. And today we're gonna handle the nitriles, because this is chapter 20 is carboxylic acids and nitriles. And the reason they are, although they are very different functional groups, but they are in the same chapter, because it's a cycle. The reaction, the prep for nitrile could be from carboxylic acid, but the reaction of nitriles lead to carboxylic acid, and so on. As I'm going today with the lecture, you're gonna find me repeating some reactions. As I just mentioned, they are kind of a cycle. This is the prep of carboxylic acid, but it's at the same time the reaction of nitrile. So please just bear with me, because I wanted to put it in the context. I don't want to assume that you just know it. Okay? So we're gonna start with the names of nitrile. First of all, what is a nitrile group? It's an R C triple bond N. This is what is a nitrile group. Let's start with a very basic how we name them. We're gonna find the longest chain with this carbon of the C triple bond N. Now, there is a misconception usually that happens in here, that the student don't count the carbon that is triple bond to the nitrogen. We should count it when we do the naming. We find the longest chain. Carbon number 1 is the carbon of the nitrile, and then we just, let's say it's an alkane, then follow it by nitrile. The other way to name that is by naming the compound as if it is coming from a carboxylic acid, like oic acid. Then we cross the ic acid and replace it by nitrile. So there are 2 ways to do that. Let's take a simple 2 examples of that. So looking at this one in here, the longest chain that contains the carbon of the nitrile, 1, 2, 3, 4, 5. So that's gonna be And on 4 we have the methyl. So it's going to be 4-methyl. Always a dash between a number and a letter. Pentane, followed by nitrile. Now, this in here, the way that I'm going to name it is I'm going to think about it as if it used to be a carboxylic acid. If that was a carboxylic acid, it is benzoic acid. So I'm going to cross the ic acid and replace it by nitrile. So that would lead to benzonitrile. So the aim of this is just for you to learn how to name the very basic nitriles without the very, very basic. And if I'm going to ask in the exam questions about it, it's going to be the very basic. No, I'm not going to go to the exceptions and the other stuff out there. Now, let's discuss the reactions of nitriles. But before that, let's do a quick review from yesterday's lecture. How to prepare nitrile? How can I get to this? What is the only method we learned how to prepare that? Where should I start from? We usually start with an alkyl halide, or this should be R, an alkyl halide. So we start with an alkyl halide where the X in here is chlorine, bromine, iodine, and we add to that the cyanide as a nucleophile. So the cyanide will replace the X. It's a substitution reaction to end up with the nitrile. Now, there are limitations for that. The Rx should not be tertiary, because if it's a tertiary, elimination will take place. Instead of the cyanide replacing, substituting the X, it will just act as a base and eliminate the X and the hydrogen from a neighboring carbon. The Rx should not be phenyl, and probably you know the reason why. A nucleophile cannot attack a nucleophile, which is the benzene ring. Not phenyl, exactly what we've seen before. Whether the phenyl is cyclic or open, so I'm going to put a cyclic one also just as a reference that it could be cyclic or open chain. So not phenyl, not tertiary. Preferentially primary. Now, one thing I just want to make sure that you paid attention to, when looking at this as a starting material and material, is there a change in the number of carbon? And yes, 1 carbon more. This is kind of the trick to tell you that you started with an alkyl halide. That 1 more carbon is coming from the carbon of the cyanide. So always when I start with an alkyl halide, add a cyanide to form the nitrile, it's always 1 carbon more. And this is kind of, I'm asking these questions because I want you to ask this question as you're looking at the exercises or the problems, is ask yourself, is there a change in the number of carbons? If it is 1 carbon more, that's a hint. We're starting with the alkyl halide adding a cyanide. So with that said, this is how we prepare the nitrile. Now, one of the reactions of the nitrile is with Grignard, which is the one which is the famous nucleophile that reacts with ketones, aldehydes, esters, and nitrile. The way that it reacts with it is this is the part, the RCC, that is coming from the nitrile, and the R prime is coming from the Grignard. So in other words, I'm going from nitrile to a ketone. So this is one of the prep of the ketone, is to start with the nitrile. Now, I know that when you look at it, it looks like how exactly that happened. So looking at the nitrile, where is the electrophilic center? Is there an electrophilic center in the nitrile? And where is that? Is it the R? Is it the carbon? of the C triple bond N, or is it the nitrogen that has a partial positive charge? It's the carbon of the nitrile. Remember that cyanide was one of the blue region of the reactivity chart of benzene. That implies it's withdrawing either by resonance or by inductive effect. And yes, there is a difference between the electronegativity between the carbon and the nitrogen, because according to the periodic table, the nitrogen is much more electronegative. So there is a inductive effect, a withdrawing inductive effect, which makes this a partially positive, this is partially negative. So what's going to happen is the R prime minus of the grain are going to attack that carbonyl, push the electrons on the nitrogen the same way it did for an oxygen, but in the nitrogen case with the H3O plus, an OH will be added to the carbon that's going to end up being the carbonyl, while the nitrogen will leave as an H4 plus, as an ammonium at the end of the mechanism. So this is one of the reactions of the Grignard. As we've seen, it's almost react with any electrophilic center except the carboxylic acid. That's the only kind of starting material till now that we said, oh, Grignard doesn't react with that. Now, this reaction, you've seen it before. I'm just repeating it. If we have a nitrile, we've seen it in the cyanohydrin. If I start with a nitrile, I add H3O plus heat or an AOH heat. So this is a hydrolysis in which the nitrile changed to carboxylic acid. In the case of an acid, it will change to ammonium. That will leave as an ammonium. In case of a base, so this is this. In case of a base, I'm going to put it in here, COO minus plus an H3. So mainly it is a carboxylic acid, but we have a base. The base will deprotonate, do an acid-base reaction with the carboxylic acid to change it to the conjugate base. So in either or cases, we're ending either with a carboxylic acid or the conjugate base, which we can simply add an H plus 2 to get it back to the carboxylic acid. Another reaction for nitriles that we've seen before is the reduction of nitrile. So we learned that this one was from the slide before, it's exactly the same. So the reduction of nitriles, we said that if I have a nitrile, I add the strong reducing agent that reduces ketones, aldehydes, esters, carboxylic acid, and nitriles. It will reduce it to R, CH2, and H2 to a primary amine. There is no change in the number of carbon during this process, because it's just a reduction. The same as the hydrolysis. There is no change in the number of carbons because it's just hydrolysis. So this is the third reaction that nitrile undergoes. And that's it. 3 reactions for the nitriles, and for the carboxylic acid, what we learned yesterday of how to prepare carboxylic acid. So from now till a couple of slides, it's only practicing on chapter 20. Then we're going to move to chapter 21, which is also related to 20. So let's get started with this equation in here, which is the best reagent. So we're asking about the best reagent to carry out the following reaction. So I'm going to change this to alphabetical. So please stop the video and do it. And I have A to be the most popular answer. A is the right answer. So you have to get used from now on, because we're at the middle of the course, that there will be more than one functional group inside the same molecule. And you have to keep an eye on any functional group in there. So in here we have a ketone and an ester. We're ending up with the ketone. Always ask yourself, what is it changing? Is there any change in the number of carbons? What exactly is changing? So the ketone is changing to a secondary alcohol. The ester is not affected. So since there is no change in the number of carbons that is connected to the carbon of the ketone, then that's not a Grignard or Wittig. It's just reduction. Because if there is a tertiary alcohol that is formed and there is a change in the number of carbon, it could be Grignard. So clearly this is a reduction reaction. So in here, the ketone is reduced, the ester is not. So I have to use the reducing agent that is more specific, that reduce ketones, aldehydes, but not ester carboxylic acid nitriles. And that would be the sodium borohydride H3O+. Now, what if I used lithium aluminum hydride? What would be the result of that? Go ahead.
It would reduce both of the ester and the ketone.
Very good. So if we use lithium aluminum hydride, which is the stronger reducing agent, it will reduce the ketone and the ester. The ketone to a secondary alcohol, the ester into a primary alcohol. So this is why we didn't choose lithium aluminum hydride. So select the major product, not the right answer. So in here, this compound has 4 different groups and functional groups. And we have to pay attention to all of them and see which one will be affected or not. We're using chromium trioxide H+, so this is an oxidizing agent. And usually what oxidizing agent do is oxidizing, so increasing, like if it is a 1 single bond oxygen, it will be double bond oxygen depending on what is the case. Let's start with in here. So this is a tertiary alcohol, and I'm adding an oxidizing agent. Tertiary alcohols are resistant to oxidation. In other words, for the oxidation to take place, the requirement is at least 1 hydrogen connected to the carbon of the OH. So this is resistance to oxidation, no change. So it's going to stay as is. This is a secondary alcohol. So secondary alcohols are usually oxidized to ketone. So I'm expecting this to change to a ketone. Now ketones, this is a ketone. They don't oxidize any further, so no change for the ketone. Now this in here is a primary alcohol. And I'm using chromium trioxide H+, so that goes all the way to carboxylic acid. It doesn't stop at the aldehyde. Even the aldehyde gets oxidized all the way to the carboxylic acid. So I'm looking for the end material will be the tertiary alcohol, no change. So these two have the tertiary alcohol, no change. The secondary into a ketone, so these seems going well. The ketone not changed, and I need the primary alcohol to go all the way to carboxylic acid. In here, C stopped at an aldehyde. So D is the right answer. Okay. So this is the oxidation, and I intentionally put all the functional groups in there that get oxidized or not oxidized as a quick revision for all the reactions of primary, secondary alcohol, tertiary alcohol, primary alcohol, ketones inside a molecule. Okay, so in here you're gonna identify the missing reagents. So what I mean by that, to go from this compound to this compound, what do you need as reagent? It could be, for example, step 1, step 2 in a Grignard, and this is a great kind of revision for for most of the reaction from this chapter and connecting it to chapter 19. So you're figuring out what is A, then to go from this one to this one, what is B, and so on. Okay, so stop the video and make sure to do this for. Okay, so I'm gonna start with the first one. So in here we're starting with an alkene. The change that I can see between the starting material and the other one is that the double bond is broken and an H and OH are added in here. The number of carbon did not change. The only change that we can see is that the C double bond C is broken. So this is mainly a hydration reaction. So we're adding an H and OH to the double bond. Is this hydration done Markovnikov or anti? Anti, very good. So the way we're looking at it is anti. So The usual reagent to add anti-Markovnikov and anti-Markovnikov addition of water is the two steps, which are hydroboration. So we're adding BH3 THF as a solvent, followed by hydrogen peroxide OH minus. So this is how we go from the alkene to the alcohol. Now, this is now a primary alcohol, and we're going to an alkyl halide. There is no change in the number of carbons, all what we've seen as if the OH is substituted by the Br. So this is a substitution reaction. The OH is replaced by a Br. So there are two methods to do that. One of them is to use phosphorus, Br3, or HBr. Either or is right. You learned that from Orgo 1, and this is why I'm putting it in here, so that as kind of a review, that a primary alcohol, we can change a primary alcohol, substitute the OH on a primary alcohol to a Br using either phosphorus tribromide or HBr. So now going from this primary alkyl halide, we're ending up with a carboxylic acid. Is there a change in the number of carbons? So this, I'm just gonna go step by step. So I'm pointing to each carbon. So yes, there is one carbon more, and we're ending up with carboxylic acid. So clearly, I need one of the methods for prep of carboxylic acid that it is one carbon more. So the two methods that we learned that we can prepare carboxylic acid from an alkyl halide clearly with one carbon more are, first to start with Rx, add the cyanide, replace the X with the cyanide. So this is the one carbon more. Can you see that? That the R now has one carbon more, followed by hydrolysis, H3O plus heat. We end up with the carboxylic acid plus ammonium. So this is one method with one carbon more, starting with an alkyl halide to carboxylic acid, one carbon more. The other one is also starting with an alkyl halide and do Grignard, magnesium, followed by CO2, followed by H3O plus at 0 Celsius. That will end me first, the Rx plus Mg gonna form the Grignard. The Grignard gonna attack the CO2 to change it to carboxylic acid, and it is one carbon more from the alkyl halide. Now the difference between the two, that this in here has a limitation, that the alkyl halide shouldn't be tertiary, not phenyl, not vinyl, that we just listed minutes ago. Not tertiary, not phenyl, halide, not vinyl. Now, looking at this in here, because it's an alkyl halide and a Grignard, there are no limitation of the alkyl halide. It could be anything, because in a Grignard, the alkyl halide has no limitation. So with that said, with this quick revision, let's go back to the alkyl halide I have. The alkyl halide that I have is a primary. So whether I use the cyanide method or the Grignard method, I'm gonna end up exactly with the same result. If the alkyl halide was tertiary, I have to choose the Grignard method over it. But in this case, either or would do. So I'm gonna put both of them for your reference. So either the first step, cyanide, followed by H3O plus heat, or magnesium, to prepare the Grignard, CO2, followed by H3O plus at 0 Celsius. And that will change the alkyl halide to carboxylic acid with one carbon more. Now the next one, I have a carboxylic acid. I'm ending up with a primary alcohol. And if I count the number of carbons, there is no change in the number of carbons. So what type of reaction is this? If I have a carboxylic acid and I'm ending up with a primary alcohol, no change in the number of carbons. It is a reduction reaction. I'm reducing the number of oxygens inside the compound, so this is why it is reduction. Now, what is a reducing agent that can reduce carboxylic acids and ketones and aldehydes and esters and nitriles? The lithium aluminum hydride. Can I use sodium borohydride in this case? No. Sodium borohydride reduces ketones and aldehydes only. So in here, I'm going to use lithium aluminum hydride followed by H3O plus. Now, going from this compound to this one, there is no change in the number of carbon. Always ask this question, it's going to narrow it down for you. I'm going from primary alcohol to an aldehyde, no change in the number of carbons. So what type of reaction is this? It's an oxidation reaction. I'm oxidizing it. And if I use a chromium trioxide H+, I'm going to take it all the way to the carboxylic acid. The reagent that we learned about, that it takes a primary alcohol to an aldehyde, is this Martin reagent. And it is, especially for the multi-steps that we're going to do soon, you need to know this reaction. I'm telling you from now, you're going to see this reaction in the exam, going from a primary alcohol to an aldehyde. So you need this Martin reagent. Now the very last step, there is no change in the number of carbons, but the aldehyde is now an alkane, or the carbon that used to be the aldehyde is now an alkane. So we learned that there is a reagent that can reduce any ketone or aldehyde to a CH2. And that's using Wolff-Kishner reaction, which is the hydrazine, OH minus, or sometimes written as NH2, NH2. Now, the aim that I put this together is to walk you kind of a quick walk through all the reactions and how to handle them. But if I were you and I'm preparing for an exam, in addition to going step by step like this, what I would do is take the starting material and the very end material, which is the alkane, and ask myself, how can I do that? Or what is the way to go from the starting material to the end material? Any question about any of the steps I've done in here? Okay, so next is a couple of multi-step synthesis. So the question in here is how to get from the starting material to the end material. As you can see, although we are in chapter 20, we're gonna build on the knowledge of what we learned in chapter 16. And that's also applicable for the exam. Yes, the exam too is not cumulative, yet we're building the reactions that we learned in the first couple of chapters. I'm assuming you still know them and you didn't just delete them after exam one. All right, so go ahead, figure out what are the steps, the reaction that is needed for that. Okay, so as usual in multi-steps, the questions are what is added, the number of carbons, the functional groups that added, and then what can we do, or what are the reactions that can lead to that. So in here, this is the starting material, so I'm mapping it. This is the benzene ring. Clearly, there is this in here that is added to the benzene ring, and there is a carboxylic acid. And this carboxylic acid is not a benzoic acid. It's not a COOH that is directly connected to the benzene ring, because there is an easy way to prepare that, which is any CH with at least one benzylic carbon. I can change that to using KMNO4 to that. This is not a benzoic acid. So I have to keep that in mind. In other words, I have to think about what are the reactions that we learned in this class that can form a carboxylic acid. We did a revision a minute ago, either nitrile from an alkyl halide, but that has limitation, no tertiary, no phenyl, no vinyl. Or Grignard, which is open from an alkyl halide, it's open. It's always like, I mean by open that there is no limitations of the alkyl halide. or primary alcohol that I'm oxidizing all the way to carboxylic acid. These are my options. So going backward, I'm saying, oh, you know what if to go backward with this, if I have a BR in here, can I use the cyanide method for this? If I'm starting with this as and the way that I figured out that this is my alkyl halide, I looked at this is the carboxylic acid, so whatever left used to be the alkyl halide. So this alkyl halide is tertiary and benzylic. This is a limitation for cyanide. The cyanide will kind of eliminate the Br and an H from a neighboring carbon, and I'm gonna end up with an alkene. So the method of choice, starting with an alkyl halide, is the Grignard method, is adding a magnesium, change this to the Grignard, followed by CO2 and H3O plus at 0 Celsius. That would replace the Br with the COOH, or the carboxylic acid. The carbon of this is coming from the CO2 that we added in there. So now going backward, does this make sense, guys? Questions about it? Okay. So going backward, I'm looking at the benzene ring and the alkyl halide I have. So I added kind of isopropyl to the benzene ring. So, and then the Br is on the benzylic carbon. So my going backward is, I have an isopropyl and I added Br to the benzylic carbon. What is the method to add a Br to this benzylic carbon in here? Or to an allyl carbon? MBS UVCCl4, which is the addition of a Br or the bromination of a benzylic or an allylic carbon. In this case, it's a benzylic. Now, going backward, how to add this isopropyl, Friedel-Crafts alkylation. So I'm doing Friedel-Crafts alkylation to add the isopropyl, but as we know that anytime we're doing Friedel-Crafts alkylation, there is a possibility of rearrangement. Now for this is the carbocation that's going to form. Is there any possibility of a rearrangement? So there is no possibility of a rearrangement. So this is the major. Actually, it's the only product that is going to form. Then MBS to add the Br, then the Grignard. Does this make sense? Go ahead.
Would you also use FC?
Go to another question. So in here, show how you might prepare this compound, which is mainly ibuprofen, the main reagent in Advil and other painkillers. Now, one thing that I'm not showing in here, and I'm not expecting that you will do that with the amount of knowledge that I taught you in this class, is that ibuprofen, this carbon in here, it is chiral. If you look at it, it is chiral. And usually ibuprofen, there is only one, so this has either R or S, and only one of those isomers or enantiomer is active in the body. The other one, if we consume it, it has a little bit of effect in our body. And this is why we really care about the R and the S. Now, in the ibuprofen case, both of them are not toxic, but some other medicine or other compounds, one can be toxic and the other will not be. In this case, it's just active or inactive. So in this synthesis, we're not gonna kind of pay attention to the R and S. We're just gonna do the reaction as it is. But if we're accompanying and we're preparing ibuprofen, most probably we have to keep an eye on the R and S and how to achieve the one that is active. So go ahead, stop the video, do that yourself and come back to it. So again, we're gonna ask the same questions. What is added, what part of the end material is the starting material. So I'm gonna circle what I can see that is this part from the starting material. So clearly these carbons are added to the para position of the isobutyl, or this group in here. And there is the COOH or carboxylic acid in there. So and this carboxylic acid is not a benzoic acid, so it's not an easy one benzylic hydrogen, I can oxidize it. So I'm thinking backward, I'm saying, okay, the same as we've done in the slide before, saying, oh, you know what? I just know the following, that this used to be a Br or a Cl or iodine, so this is used to be the alkyl halide. The way that I figured it out, that this is the carboxylic acid, so always if I start with an alkyl halide, 1 carbon more, whether I use the cyanide method or the Grignard. Now I have to ask myself which one I'm gonna use, or is there no preference? Either or would work. So in here I have a benzylic and a secondary alkyl halide. Now cyanide method would work, but the yield that's gonna be, so if you put the cyanide method, I can put it as a wrong method because the yield is good, but it's not as good because it's secondary as good as the Grignard. So I'm gonna use, since I'm using the best method, I'm gonna use the Grignard one. But in the case of tertiary, it's definitely a no for the nitrile. So I'm gonna add magnesium to prepare the Grignard, to change this alkyl halide to a Grignard, followed by CO2. This carbon in here is coming from the carbon of the CO2. And the third step is adding the H3O plus at 0 Celsius to end up with a carboxylic acid. Now, going backward is saying, okay, how I'm gonna prepare the Br on a benzylic carbon? Probably the first thought that's gonna come to the mind is, oh, it's a benzylic carbon, so the easiest way is to use the bromination of a benzylic or allylic, which is MbSUVCCl4. Now, in here, it's not gonna work. And the reason behind that, if I have this in here, and let's say I added, this is my alkyl, the other alkyl halide, and I added MbSUVCCl4, I have in this case 2 benzylic carbons. And if I add one equivalence, it's 50 to that one or 50 to this one. I can do the one equivalence trick, but it's not gonna give me a better yield or one of them where I want it to. And this is where we're like, okay, you know what? Is there any other method where I can prepare this alkyl halide? And one of the things that we can do is going backwards saying, oh, yeah, we can usually substitute an OH with a Br that we've seen in a couple of slides before. If I have an OH, I can replace that with a Br using phosphorus tribromide. So all what we're doing here is a substitution of the OH with a Br. So this is a secondary alcohol. In here we have the OH as secondary. One of the ways to prepare a secondary alcohol without changing the number of carbons is the reduction of a ketone. So I'm going backwards saying, okay, this used to be a ketone in here, and I reduced it. And I can reduce a ketone using sodium borohydride or lithium aluminum hydride. So I'm gonna use, in this case, this, or lithium aluminum hydride. So that's the reduction of a ketone to a secondary alcohol. Now, how to get this aryl ketone? How can I add a C double bond OCH3 to a benzene ring? It's a Friedrich-Crafts acylation. So I can, this is how we can prepare an aryl ketone. So we know that whenever we're doing Friedrich-Crafts acylation, there are limitations. There shouldn't be a deactivator meta-director on the benzene ring. This in here is an activator, ortho, and para-director, so it's not part of the limitation. This is an ortho para-director, so it can direct this C double bond OCH3, or one of the product is having that aryl ketone on the para. And this is why this reaction will take place as is. Does this make sense to you guys? Okay. So in other words, if I wanted the Br on the benzylic, one option is MbSUVCCl4. If that option is not, for a certain reason, it cannot be used, we can start with an aryl ketone, then reduce it to a secondary alcohol, then replace the OH with a Br. questions about any of the steps? Okay, so with this we're done from the carboxylic acid chapter. Now we're gonna start with chapter 22, which is not far away from the carboxylic acid. Actually, this chapter is about carboxylic acid derivatives. And that include a couple of them. This in here with an X, where X is a chlorine or a bromine. We call it acid halide. We've seen this in Friedel-Crafts acylation, where we use the acid chlorides. A minute ago, we used one of them. We call this anhydride. So if you look at it, it is a C double bond O, C double bond O, and an oxygen in the middle. The third acid derivative is, we've seen that before, which is an ester. It's a C double bond O, OR prime. And the fourth acid derivative is an amide. So these are the four acid derivatives we're going to discuss today: acid chloride, anhydride, esters, and amides. And we call them acid derivatives because it looks like the OH is replaced with something else. Like in here, the OH of a carboxylic acid is replaced with a chlorine or a bromine. In this case, it's replaced with this one, with an OR prime, with an NH2. But all of them have a C double bond O in them, which is close to the carbonyl of a ketone or aldehyde. Now, the common reaction that an acid derivative is going to undergo is a nucleophilic substitution. From the name, we're gonna add a nucleophile. The nucleophile gonna replace the Y, where the Y is either the OR prime of an ester, or a chlorine bromine of an acid chloride, or OC double bond OR of an anhydride. And the mechanism goes this way. So I'm gonna draw the mechanism in general. We're gonna have a nucleophile, as you probably expecting what's gonna happen next, that this having a partial positive charge, the nucleophile will attack the carbon of the carbonyl. The pi bonds, the electrons of the pi bonds, gonna reside on the oxygen. So we ended up again with a tetrahedral intermediate. We call it tetrahedral because the shape of it is a tetrahedral, because it's AX4. Now this step is very similar to what we've seen in the ketones and aldehyde. It's exactly the same step. Now I want your attention about the second step, which is the difference between ketones, aldehyde, and this. When the lone pairs of the oxygen, in this case the lone pairs of the oxygen, come back, they kick out the Y. The reason that it kicks out the Y, that the Y in acid derivative is a good leaving group. It's either a Cl minus, I minus, Br minus, or R prime O minus. So it is one of the good leaving group. While in the ketone, there wasn't a Y, there wasn't a good leaving group, it was an R. And R, if it leaves as a carboanion, it's not a good leaving group. So in other words, we're starting, if you look at the starting material and end material, all what we've done through this is replacing the Y with the nucleophile. This is why it's called substitution. And knowing the mechanism gonna help you a lot in the upcoming reactions, because all what I'm gonna do in all the other reaction is add a nucleophile. The nucleophile will substitute the Y. And it's very predictable. Even if you don't memorize the reactions, you can just predict them because it is very easy. The nucleophile substitutes the Y, the leaving group in there. Does this make sense as a mechanism? Very good. Now, here is the electrostatic map, the 4 different acid derivatives and the reactivity chart. As you can see, according to this reactivity chart, this one is the most reactive compared to the least reactive in here. So according to this chart, acid chlorides are more reactive than acid anhydrides, than esters, than amide. And the question is, how would you explain this fact? So stop the video, think about what the factors that affected that the acid chlorides are always more reactive than acid anhydride, esters, and amides. The Cl is the best leaving group. That's a good point. The Cl is a good leaving group, so it will be reactive. That's a good point. Compared, for example, to NH2 or NH3, that's going to leave in the amide. So I'm taking the both extremes because it's easier to see. Other than the leaving group argument, requirement is to have the carbon of the carbonyl more electrophilic, more in need of electrons. So if we look at the chloride in here, we know that halogens are the most electronegative in the periodic table. So this Cl, in addition that this carbon is carbon of the carbonyl, it has a withdrawing group, which is the oxygen. Add to that the Cl. Add to the mix the Cl that is also withdrawing the electrons. So think about this, that this has more need, this carbon of the carbonyl is more electrophilic, more in needs of electron because of those two withdrawing groups. So this is more electrophilic. I'm going to go directly to the other extreme so that you can see it, which is the nitrogen of the amide. Also, the nitrogen is an electronegative atom, right? And it should withdraw the electrons, but instead of that, in addition to that, that nitrogen, it has another effect. If you remember the NH2 and the reactivity chart of the benzene, it was in the purple region of the reactivity chart. It was one of the donating, and it was donating by resonance. So this in here, this carbon of the carbonyl is not as electrophilic as that of the acid chloride. Why? Because add to the mix the resonance structure. So it has a resonance structure that is stabilizing it, or you can think about it from another point of view, that this carbon is not that electrophilic because sometimes it is double bonded with the nitrogen. So, and the others are somewhere in between. So we have the acid chloride being very electrophilic. It has a good leaving group. If we want to discuss it from a leaving group point of view, we can also discuss it from the point of view that we have a Cl, which is withdrawing, making the carbon of the carbonyl more electrophilic. While the amide, it is donating by resonance. Now, if you want me to talk about the ester, it's also donating by resonance, but it is less donating than the nitrogen because the oxygen wouldn't prefer to have a plus charge compared to the nitrogen. And in this one in here, the oxygen kind of is also donating, but it's donating to both carbonyls. So it is kind of adding to both of them. So from now on, what I need you to know, and it is important for your understanding in this chapter, that acid chlorides is the most reactive, followed by anhydride, followed by ester, and the least reactive of all is the amide. And that's very important because I'm going to explain it in the slide after this, in 2 slides, why would we need to understand this reactivity and the importance of that. Okay, so let's do a question on this. So rank the following acid chlorides. So all of them are acid chloride from the most reactive to the least reactive. So you're choosing alphabetical, either A, B, C, D. So stop the video and do it. And I have A to be the most popular answer. A is the right answer. So in here, all of them are acid chlorides. So I'm not comparing different acid derivatives. All of them are the same. The difference is mainly the group, the R group that is there. And here we have methyl, small group, compared, I'm going to take the extremes, small group compared to a tertiary-butyl that is close to the carbon of the carbonyl of that acid chloride. So the main contributor in here is the steric hindrance. So here I have 3 acidic chlorides. The difference between them is that one is acidically hindered more than the other. And the one that is least acidically hindered is going to be the most reactive, because the nucleophile, it's easier for the nucleophile to attack the carbon of the carbonyl. So we're starting with 3 being the least acidically hindered as a carbon of the carbonyl, then 1, then 2 to be the least reactive because of the steric hindrance. So the main idea in here is steric hindrance taken into consideration in each one of these. Does this make sense to you guys? Okay. Now, this map in here, it shows the least reactive being the amide being the least reactive, and acidic chloride to be the most reactive acid derivative. And as you can see, looking at this chart in general, there is an arrow going from the acidic chloride to the anhydride, from the acidic chloride to the ester, from the acidic chloride to the amide. But we don't see any arrow from the amide to the acidic chloride. And that's an indication that we can prepare the acid derivatives with lower reactivity from the one with the highest reactivity, but not the other way around. And this is why it is important for you to know that acidic chloride is the most reactive. From it, I can prepare the ester and I can prepare the amide. While I can prepare, if I start with an amide, I'm not going to be able to prepare acidic chlorides. The same when I get to the ester, I can prepare amide from an ester, but I can't prepare ester from an amide. And this is why you need to know the reactivity, because it's going to make your life much easier if I give you an amide going to an acidic chloride. So what we're going to do next is go over the reactions. And as I said, there is a very easy way to figure it out. Mainly, I'm going to add a nucleophile. The nucleophile going to substitute the leaving group. So let's start with the first one. We're going to handle the reaction. Today, we're going to handle the reactions of acidic chloride. So if I start with an acidic chloride, it could be also bromide or iodide, but I'm referring to the acidic chloride in this case. And I add H2O and pyridine just as a catalyst, and I'm going to talk about it. I'm going to end up, and in here I'm going to use a different color for you to see it. To give this in here. So if I start with an acidic chloride, add H2O to it, the expectation is the water being the nucleophile, it's going to replace the Cl. So it's going to be somewhere right here. Then the Cl minus that left the acidic chloride will pick the hydrogen to be an HCl. So we're ending up with a carboxylic acid and an HCl. Now, probably the question is, oh, why do we need pyridine? So the pyridine is needed as a weak base to neutralize the HCl that is forming. Because if I have H2O as the nucleophile and I start having HCl in the beaker, it's going to be reacting with it to form hydronium ion plus Cl minus. Would the hydronium ion be a nucleophile? No, because it has a plus charge. The oxygen has a plus charge. So the aim in here is to add the pyridine. Every time we're doing a reaction, you're going to see this in every slide, in the upcoming slides. Every time we have an acidic chloride as a starting material, we're going to add pyridine to neutralize the HCl that will form. Okay? So this is the first reaction that an acidic chloride can undergo. Mainly, if you think about it, we're going back to the carboxylic acid. We're starting with an acidic chloride. It's hydrolysis. We're going back to the carboxylic acid if we add just H2O. And that's at room temperature with pyridine, no need for heat. Why? Because acidic chlorides are so reactive and they will do it at room temperature. Now, later on, when we get to the amide, which is the least reactive, we're going to need a little bit more to hydrolyze it, to take it back to the carboxylic acid. Now, I'm going to ask you the question, what should I add to change an acidic chloride to an anhydride. I'm asking you, although I didn't explain it, because there is a way to figure it out based on the main mechanism. So the whole mechanism in this chapter, I add the nucleophile, the nucleophile will replace the leaving group. So all I have to determine, oh, this is the leaving group. I'm going to compare it. It is replaced by this one. That's my reagent. So as simple as that. Even if you don't memorize the reaction, you can figure it out as long as you know that this is an acid chloride nucleophilic substitution reaction. Okay. So as we said that from acid chloride, I can prepare anhydride, all the lower reactivity one, and I can also prepare an ester. What should be the nucleophile, or what should be the reagent in this case? Again, I'm going to compare. The starting material is an acid chloride. It's replaced by ROH, R prime OH. So the reagent will be alcohol plus pyridine. Pyridine is to neutralize the HCl that's going to form during the reaction. So there will be HCl plus pyridine, which is going to end up with the pyridinium chloride in here. Now, for this one, the primary alcohol is much reactive than secondary than a tertiary. So there is a preference for a primary alcohol more than secondary, more than tertiary. So the last one, as you might predict, is how to prepare the amide. Actually, before we go to the amide, if I have an acid chloride and I start with this molecule in here and I add pyridine, and let's say I have one equivalence of the acid chloride. At a case like this, where I have a bifunctional group, two alcohols in the same compound, this is a primary and this one is secondary. The one that's going to react faster is the primary, and that's based on primary reacts more than secondary, more than tertiary. Now, if I add two equivalents of the acid chloride, both of them will react. There is no preference in there. So in here, the one, because I'm using one equivalence, this O, the oxygen will attack the carbon of the acid chloride, ending up with that, with the CO. So we have oxygen in here. So this attack the carbon of the carbonyl, the Cl will leave, ending up with the ester in here, and this OH, the secondary alcohol, is not affected in there. Now, if I add two equivalents, both of them will react. Now, the last reaction to prepare the last acid derivative is the reaction to form an amide. So we're starting again with an acid chloride, ending up with an amide. The Cl is replaced by NH2, so I'm going to add NH3 with pyridine. Again, the role of pyridine is to neutralize the HCl that's going to form, or two equivalents of NH3. The reason that I can use two equivalents of NH3, because NH3 itself is a weak base, and it can neutralize the pyridine, the HCl that is formed. So the pyridine is to neutralize HCl formed during the reaction. And usually it is preferable to use two equivalents of the same base instead of mix and match. Sometimes there will be an amine which is very expensive, that a 1 milligram is $100 So the easiest way is then at that stage is to use a 1 equivalence of the amine, then a pyridine, and then I'll use the pyridine as my base. So we're gonna stop right here. I